Okay, so now let us turn to plane strain problems. In plane strain, we have u3 equal to 0 and all quantities, no quantity varies with x3. So del x3 of all quantities is also equal to 0. This is your plane strain assumption. Um, the equations that we are going to derive are can be converted to plane stress very easily. You must have learned that in your elasticity courses. And I will not explain these equations. These are Navier's equations. These two are Navier's equations. For plane stress, the three Navier's equations reduce to two, and these are those equations. We have replaced x1 by x and x2 by y for the plane problems. And please look up your Navier's equation. Navier's equation, let me write it down. So this is lambda plus mu this is your Navier's equation. Okay, this is your Navier's equation, and from this Navier's equation, with the assumption that u3 is equal to 0 and del x3 is equal to 0, you get to these two for plane strain or plane stress problems. Let's stick to plane strain. Okay, so now we assume that the displacements are analytic. Displacements make up an analytic function. The x displacement is u, the y displacement is v, and they together make up an analytic function d. Displacements have to be analytic for smoothly varying differentiable displacements. We need d to be an analytic function. So we assume that d equal to u plus iv is an analytic function whose real part is the x displacement and the imaginary part is the y displacement. So having done that, we can now write the Navier's equation, the two Navier's equation together into one equation. We can club them into one equation. So this is what we do. We multiply this by I on both sides and add it to this equation. So this equation plus I times the second equation, and that will give me this mu remember d is u plus iv. This comes from the first term, and from the second term we get lambda plus mu of equal to 0. So now this you should recognize from the definitions that we gave at the beginning as del z bar. So this is del z bar. What is this? Now this you can easily show that if d is u plus iv, then del z of d is half of u plus iv. This is del z of d, and then this can be written as half of so this times this, and then this times this gives you the real part, plus this times this, so del u del y minus I, and then this times this plus I del v del x give you the imaginary part. So this is plus I minus del u del y plus del v del x. This is the imaginary part. So this part, the real part of del z, del d del z is this. Therefore, if I write, I can write this as del d del z plus del d del z conjugate and half of that. Okay, so this quantity is half of del d del z and plus del d del z conjugate. This is not del d bar del z, this is del d del z whole conjugate, you must remember. Now, what is this? Let's erase this. So del square is del del x plus I del del y times del del x minus I del del y. You will remember that this is del del z bar and this is del del z. So this is del del z bar of del del z. So this quantity here is del del z bar of del del z of d. Okay, so now we can club the terms together, and this is what we will get. We will get del del z bar of this whole thing. Here you must remember this is conjugate of this whole thing, not d bar dz. D bar dz is equal to 0, but this is del d del z whole bar. Okay, so now this quantity del del z bar of this quantity is seen to be 0. That's the result from Navier's equation, and therefore since del del z bar of this is equal to 0, this whole thing must be an analytic function, because for analytic functions del del z bar is equal to 0. So what we do is we multiply both sides by 2. Why we multiply both sides by 2? It will there's no very deep reason for that. It just makes the final equations a little bit nicer. That's why in foresight we multiply it by 2. So this quantity we call it f prime z. So fz is an analytic function, so f prime z is also an analytic function. So this is your f prime z, and we take conjugates. Now we can derive another equation by taking conjugates on both sides. So this will become conjugate, this will become conjugate, and conjugate of conjugate will take this away. So this is what we will get if we take conjugates of both sides, and this will also become conjugate. So so these are the two equations. These are the two equations that we have, and now we will use this simple facts. So real part of del del z is half of this, we know. Imaginary part of del del z is 1 by 2i times the del del z minus del del z conjugate. Okay, so once you do this and you put it back, you add these two equations, you will come up with two equations after a bit of tedious calculation, which I'm not going through, but you might want to, where I get an equation for the real part of del del z and an imaginary part of del del z. Let me repeat what we just did. So let me erase this and make it clearer. So we had argued that since del del z of this whole thing is equal to 0, this must be equal to an analytic function, and that analytic function we have taken as f prime. Now we take the conjugate of this and get another equation, using these two equations and using the fact that the real part is this and the imaginary part is this, I will be able to separate the real and imaginary parts of del, del d del z, and they are these two. So this is the real part and this is the imaginary part of del d del z. Remember, d is actually u plus iv, which contains our displacements in the x and y directions. Now combine the two, and when you combine the two, write the real part plus I times the imaginary part, and just adding the two, this is what we will get. This is what we will get. Okay. Now f prime is a analytic function, so f is also an analytic function, and all derivatives of f would also be analytic functions. But now what we have here is this whole thing is simply del z, okay, which is same as d dz, because or equal to d prime, because d is only a function of z, it's an analytic function. Now we integrate. When we integrate, we have to remember that this quantity is f prime z, and it is only a function of z, okay, and this quantity is f prime bar z, which is only a function of z bar. So when you integrate, this will become fz, and this will become z times f prime z bar. That is what integrating with respect to del z would do. And then you would get another function which is phi z bar, which is a function of z bar only. It's a function of z bar only. That function will come as a constant here. This is another analytic function phi, and phi z bar would come as a constant here, because you have del z. You have del z. You are integrating with respect to z, and you can have a constant that depends on z bar only, and phi z bar depends on z bar only. So this can also be written as phi z bar. So it's a function of z bar only, and that will appear as a constant because you are integrating with respect to z. So that's how we get to this equation, by integrating it with respect to z, integrating this equation with respect to z. You have to remember that this is del d del z. I'm integrating with respect to z, so this becomes f prime, z becomes fz. This is a function of z bar, so it becomes z f prime z, and you have a constant phi z bar, which is a function of z bar only. That comes because you are so now you have two analytic functions, f and phi, that need to be determined. So d is determined in terms of f and phi both, and now we just rearrange the equations. So rearranging the equations, we define two new functions. So omega z is, capital omega z is an analytic function that is related to the fz through this relation. This is just to make the equations nicer. We could have worked with fz and phi z is related to small omega z through this equation. So we have just redefined, we just use these constants to redefine the functions, and then we get a set of slightly less formidable looking equations. So this is how your displacements are given by. So your displacements are now given in terms of capital omega z and small omega z bar, and this is the displacement equation. The real part of this is u, the imaginary part of this is v. Okay. Now once you have got the displacements, then you can derive the stresses using the constitutive equations, and these are the stress equations. So in the antiplane shear case, you had one analytic function to be determined. Here you have two analytic functions to be determined. And if you can determine capital omega z and small omega z, then you have all the stresses and all the displacements at all points on the body. There are no differential equations to be solved. These are all algebraic equations. And these were first proposed by Mushkelishvili, and then Kolosov translated them into English. Mushkelishvili was a Russian mathematician, and these two stress equations and the displacement equation together form the Km equations, or the Kolosov-Mushkelishvili equations. Okay, so now the problem is, how do we find capital omega and small omega? Once we have found them, then we can find everything. And it will turn out that in certain problems, these are really easy to determine. These things are really easy to determine using the machinery of analytic functions. But to do that, we have to understand how the boundary conditions turn out. So these are the stress equations, and we will now write the traction boundary conditions in terms of these stresses. So now there are two components of the traction, Tx and Ty. Again, use the Cauchy relation, Ti equal to sigma ij nj. Use this, and you will see that for the plane strain assumption, there are only two tractions, Tx, which is sigma xx nx, sigma xy ny, and Ty, which is sigma xy nx, sigma yy ny. These two are the traction equations, and then you can club them together into one single variable t, complex variable, as Tx plus Ity. So just multiply this by I, on both sides add, and then nx and ny, remember we had already derived, nx is dy ds, and nx is dy ds, and ny is minus dx ds. Putting that in, this is what we get. This just follows from here. Now it turns out that this quantity here, this quantity and this quantity can easily be extracted out of the Km equations for the stresses. So these are the Km equations for the stresses. If you add these two, you will see that sigma yy cancels out, and you get sigma xx plus 2i sigma xy. If you subtract them, sigma xx will cancel out, and you will get sigma yy and sigma xy on the left hand side. On the right hand side, you will get a combination of these analytic functions, which are not yet determined. These are arbitrary analytic functions for the time being. So this part can be got by adding the Km equations, and this part can be got by subtracting the Km equations. Let's do that now. So adding the Km equations, this is what we will get. Subtracting them, this is what we will get. Now look at these two terms, which are common here and here. These two terms are common, and these two terms we can now these are arbitrary analytic functions. So these two terms we can write as del z of omega z is omega prime z. Del z of z omega prime bar z is just omega prime bar z, because this is a function of z bar, and then this is a function of z bar only, so that del z of this will go to 0. So I have just added this term. In hindsight, I know that I'm going to use this in a clever fashion. I am not going to use it. Kolosov and Mushkelishvili use this, so I'm just going to repeat what they did. Now look at these two terms. This term, these two terms are also appear in both the equations, and they can be expressed in almost a similar format. So what we can do is the second terms, these are the second terms, and we can write it as del z bar of z omega prime z bar. So take a derivative of this with respect to z bar. This doesn't get affected. This gets affected. So this term is del z bar of this, and this term is the del z bar of this. Again, this is a function of z, and del z bar of this is equal to 0. Now this function and this function are both the same, so we give it a different name and we call it gz. So gz is this, so that this is del z bar of gz, whereas this is del z of gz. Okay, so these are the two equations, and now this will become this is del g del z minus del g del z bar, and this is del g del z plus del g del z bar. So this is what we will get for sigma xx plus I sigma xy and sigma yy minus I sigma xy. Now we can calculate the fractions. So we plug it in here. This is del g del z minus del g del z bar, and this is del g del z plus del g del z bar, right? So if you do that, write the fractions. Nx is del y del s. This is nx. This is your ny. Little bit of manipulation will show you that t is equal to minus I del g del s. So the manipulation is pretty simple here, and you get t equal to minus I del g del s. The force is traction times ds. Again, the thickness out of plane is equal to unity. So if you write this as minus I del g del s into del s, will give you minus I g at s2 minus g at s1. You multiply by I on both sides, so this becomes 1, and then IFS is equal to, you write the definition of G. Definition of G is this whole quantity evaluated at S2 minus this whole quantity evaluated at S1 would give you I times the total force that acts on a part of the boundary. Wherever the force acts, the total force will be given by this. This will be a known quantity. This will be told to you where the forces are applied on the surface of the body. So these forces will be related to this combination of the analytic functions that we have. Now, note a important thing. This combination of terms, capital omega z, z, omega prime z bar, and small omega z bar, also appear in the KM equations for displacements. So in the same order, so this, and this also appear in the displacement equation, except that in the traction equation you have 1 here, and in displacement equation you have 3 minus 4 nu, which comes from plane strain. So I can now write the boundary conditions in a combined manner. So I can write the displacement boundary condition. This is the displacement boundary condition. So D might be specified at some parts of the boundary. So this is the displacement boundary condition. And then I define this function hz, where alpha is equal to 4 nu minus 3 in case of the traction, and in case of the displacement, and alpha is equal to 1 in case of the traction. So if you have specified displacements, then it will be minus hz with alpha equal to 4 nu minus 3. And if it is if tractions are specified, then tractions are specified as tx star and ty star, then the total force, I times the total force, is hz with alpha equal to 1. So this is the way the boundary conditions can be clubbed into one set of equations, with a different constant. So they can be written in a unified manner. And these boundary conditions will serve as starting points for guessing or determining these analytic functions. Remember, once you have determined these analytic functions, guess these analytic functions, solution to a boundary value problem in elasticity is unique. So you have, if you can determine these functions, you know all the stresses and displacements all over the body, and that will be the answer to the problem because it's unique. Okay. Now, small addition to this: we sometimes need to solve problems in cylindrical polar coordinates, problems that are defined on disks or annuli. So in those cases, we would need a version of these equations, the stress equations and the displacement equations, version of the Km equations in terms of sigma RR, sigma R theta, and sigma R sigma theta theta. So these will replace sigma xx, sigma yy, and sigma xy. So to do that, it's a plane problem, so we can easily transform sigma xx, sigma yy, and sigma xy into the cylindrical polar coordinates. And if we do that, we can derive the Km equations in cylindrical polar coordinates as well. Obviously, the trace of the stresses, sigma xx plus sigma yy, the trace of the stresses remain the same. And if you add sigma, if you look at the Km equations, if you add these two, then you get sigma xx plus sigma yy. This term, these two terms cancel out because they have minus here and you have plus here, and you get 2 times omega prime, capital omega prime z bar. So that is what sigma xx plus sigma yy, the trace of the stress tensor, is. The trace is an invariant, so sigma RR plus sigma theta theta would also follow the same equation, here, right? Now you can transform sigma RR, sigma theta theta, R theta to sigma xx, yy, xy in this manner. You must have learned stress transformation, and you can easily do the stress transformation and see that this is indeed true. And then once we have done this, we can write down the second Km equation, which is sigma xx minus yy plus 2ixy, just by replacing these terms, and this is what we will get. So you get the same combination, RR theta theta plus 2ir theta, except that you get this extra 2 e to the power 2i theta. Okay. This 2 should remind you of Morse circle, where you had to turn by 2 theta whenever you wanted a transformation by an angle theta, but that's a different story. So the first Km equation, which is for sigma xx plus sigma yy, remains unchanged in cylindrical polar coordinate because that involves the trace of the stress tensor. The second also remains unchanged except for this e to the power 2i theta that comes about. So we can take it to the other side, write it in the same way as the Cartesian. So sigma RR theta theta 2i theta is the same thing as the Cartesian with e to the power minus 2i theta added. Similarly, we can transform the displacements also. So you can write u plus iv. We have a displacement equation. Remember, 2 mu d. We have 2 mu d, and d now expressed in cylindrical polar coordinates would be ur plus iu theta, and with this e to the power I theta. So we can write it. So this is now your d in cylindrical polar, and 2 mu d is the same thing as in the Cartesian with this e to the power minus I theta that is taken to the other side, and this is where you multiply. And similarly, you can show that in the cylindrical polar coordinate system, the traction, the total force IFS, is given by the same combination of the analytic functions derived, evaluated at S2 minus that evaluated at S1. It's exactly the same as in Cartesian system. So this completes uh, our discussion on the Km equations. So the Km equations, there are three Km equations, remember. Um, so one for displacement, which is this, and two for stresses, one for the trace of the stress and one for this combination of the stress. There are two functions to be determined, capital omega and small omega, and they are generally determined by this consolidated unified boundary condition where uh, 2 mu times the specified displacement is minus hz, and I times the specified traction is equal to hz evaluated at s2 minus hz evaluated at s1. hz is the same function in both cases, except for this constant alpha, which is a real constant. It is 4 nu minus 3 in case of the displacement equation, and it is equal to 1 for the traction equation. So these are how the boundary conditions for both displacements and tractions are specified in terms of these analytic functions, still undetermined. And if you work in cylindrical polar coordinates, then the first equation remains unchanged, and the second equation has e to the power minus 2I theta multiplied on the right hand side. The displacement equation remains unchanged except that it's multiplied by e to the power minus I theta. The traction boundary conditions as well as the displacement boundary conditions, the traction boundary conditions remain unchanged as well. Displacement boundary conditions obviously will have this e to the power minus I theta added on the right hand side. So this is all about Km equations, and now we will see how these set of equations can be used to solve problems, and especially problems involving cracks, and that we will do in the next video.